Hey everyone, today we're going to take a look at law of cosines. So yesterday we learned about law of sines, which can be used to relate um, some angles and sides within oblique triangles, so non-right triangles. And today law of sines is going to be similar. We're going to get some other useful tools for when we have a non-right triangle and being able to relate all the sides together. So previously, um, in a right triangle, looking at something like this, we could say, okay, I know a squared plus b squared equals c squared. And I want to be able to generate some form of formula that can be used to relate the sides and angles in the triangle that I have below, the one that's got a, b, b, c, c. So, we're going to work to derive law of cosines using this diagram. Once we have it, we're going to be able to determine the third side of a triangle when we know two sides and the angle between them. So generally that's kind of called side, angle, side of a triangle. And then we'll also be able to determine angles in a triangle if we know all three sides. So we might kind of consider that side, side, side. So here, and this kind of doesn't really fit, um, here in our derivation, this is going to be us coming up with law of cosines, which can be relatively tricky, but it's not something that you're going to be kind of asked with doing. It's just the proof of, why this thing exists or why we can write it out in this particular way. So what we're going to do is, again, I'm trying to come up with an equation that relates A, B, C, and maybe some angles here. So to start this, I actually need to create two right triangles. So I'm going to drop this down, which is an altitude or the height of this particular triangle. And I'm going to label this point. So we have H here. I'm going to label this particular point where they intersect as point D. And that's going to help me basically refer to a couple of triangles here. And then the last little piece that I want to do is to say, we'll call this X, this distance here, this shorter side of C, and we'll call that X. And then that makes this longer side C minus X. Okay, right? Because C is that whole distance from A to B, or from angle A to angle B. So if I take X away, I'm left with C minus X. All right, so this now gives me the ability to write all the equations that I actually have to. And because I have right triangles, I can kind of go back and use just some basic Pythagorean theorem on this. All right, so the first thing I'm going to say is if I were taking a look at triangle, let's say ACD. Okay, so and I'll just try to do some highlighting of that particular triangle. So that's A, C, D. That's that triangle there. And I wanted to come up with an equation for that. I could say, all right, that is going to be b squared equals x squared plus h squared, right? That's just our Pythagorean theorem at that point. And maybe I'll get rid of this equal sign if it's a little confusing. So I can get that from triangle ACD, and that's the triangle on the left. The triangle on the right, I can call triangle BCD. And my Pythagorean theorem there is going to be a little bit more confusing, but I would just say, okay, a squared equals c minus x squared plus h squared. And if I do a little bit of work on this one, I'm going to expand this c minus x squared, so that's c minus x times c minus x. So I get c squared minus 2cx plus x squared plus h squared. Okay, so that's basically just foiling that out. And then if I'm taking a look at this, I have some pieces that like I have made up in this problem, right? Anything that references x or h is really something that I've created and I kind of want to do away with. So I can do that by substituting in this equation into here, that helps me get rid of kind of a bunch of them, right? So if b squared equals x squared plus h squared, and in this lower equation I have x squared plus h squared, then I can substitute those out. So now this equation is going to look like c squared, and I might even just put this a little bit earlier on. So that b squared that I just put in is x squared plus h squared. I just moved it around a little, and then I have this minus 2cx here. So I've almost arrived at an equation that doesn't include anything that I've kind of made up in terms of x or h, and is just the original components of the triangle. The only remaining piece of this that I want to see if I can get rid of is this x. Okay, so that x, if I wanted to, I could say, another statement over here, that the cosine of a is equal to x over b. Okay, so cosine is adjacent over hypotenuse. So the adjacent side to A in that tiny green right triangle is x over b. And then I can solve that for x. So I get this. So b times the cosine of A is x. And that is going to allow me to kind of finish what is my law of cosines. Okay. So, just for kind of keeping, actually, no, the order's pretty good on that. That can be like slightly rearranged, but this is our law of cosines. And it can come in like different flavors here. So this would be if kind of my important angle was A, and maybe I knew the side across from it. But this angle and this side, the side that's kind of on the opposite side of the equation, go together. So if I wanted to, we can do this for any angle in that triangle. So I could say b squared equals, the things out in front are the sides that aren't kind of on the left-hand side. So if I have b squared on the left, this is going to be a squared minus c squared. And then this is minus 2ac cosine b. And we could also do the same thing. Okay, so these three different variations are the law of cosines. And it can be used to relate all, sides and angles in a non-right triangle. So before we only had Pythagorean theorem, whereas this is going to give us some tools to be able to figure out some missing angles or some missing side lengths when we have those. So let's take a look at how we can use this to find a missing side length. So here, I've got things like pretty well labeled. I might just add in some of these, helpful little tidbits here. So the side that I'm trying to figure out is that little c side. So I'm going to use actually this third variation. Like all the letters are just already lining up with this particular problem. So once those labels are in place, I'm just going to be plugging in everything that I know and then seeing if I can determine what the end result is here. So looking for c, so I can say, okay, c squared equals a squared plus b squared. So that's 8 squared plus 11 squared minus 2 times 8 times 11, and then this is times the cosine of 37 degrees. So all of these, pieces here, 8 is my A, 11 is my B, so that just goes right into my equation. C is the side that I don't know, so that's on the left. And then this C here, it's kind of hard to tell with C, but this is our capital angle C, or our angle. So that's kind of why it looks like that. So let's see, I'm kind of in Desmos at the moment. So I'll see if I can switch this to degrees and then type this in and see what we get. So I'm typing into my calculator or into Desmos this equation. So it looks like I got, in this particular case, 8 squared plus 11 squared minus 2 times 8 times 2. Okay, yep. So this is c squared equals 44.440. And then in order to get c, I just need to take the square root of both sides. So I'm going to say square root of that. So I get c equals 6.666. Spooky. Yeah, and checking the reasonableness of my answer, that looks good. You know, this side looks like the smallest, it's across from the smallest angle, so it should be the smallest side. And that is how we can use law of cosines for finding a missing side. Using law of cosines to find a missing angle isn't too much different. I'll probably start with at least labeling my sides here. And I'm getting these just from, my angles are already labeled here, which is kind of nice. If you are dealing with a triangle that doesn't have sides labeled, just choose an A, B, and C, and know that, side A needs to be across from angle A, but we should have picked up on that from law of sines anyway. So here again, it looks like I'm going to use because I'm looking for angle C, it looks like I'm going to use that last case of law of cosines. So if I just rewrite that, and I might have just rewritten it slightly different from above, but this is going to be minus 2 times A times B times cosine C. So let's plug in everything that we know and then see kind of what we're going to be still struggling with after the fact. So I end up with 8 squared equals 5 squared plus 9 squared minus 2 times 9 times 5 times the cosine of C, which I don't know. So this looks a lot like I just need to solve kind of a larger equation. So I'm going to evaluate these. So 8 squared, 64. This is 25 plus 81. This is going to be minus 90 cosine C. Hopefully I didn't screw up any of that mental math. And then continually trying to solve here. So this is going to equal 106. I'm going to subtract 106 from both sides. Okay, it's super early, so let's not screw this up, and let's plug it into a calculator. 64 minus 106, negative 42. I'm going to divide both sides by negative 90. So I'm getting 0.4666. Maybe I'll just go one more here, call it cosine C. And then similar to law of sines, when we're left in this position where I have cosine of something equals this, I'm going to use inverse cosine then to figure this out. So let's do arc cos. So if I do that, I end up with C equals 62.186, and that is this angle. All right, so because these kind of take a little bit longer, I want you to do problems 1 through 9 odd on that worksheet attached. And the answers are there, so you can kind of double check as you're going along. All right, thanks.